In this example, we are taking some measurements of a biomarker, whatever this marker is. So here are our measurements. And when we are looking at these data, we notice that, yes, they are all in the same range. Well, there are some data that are a little bit larger. And so our suspicion is that probably the distribution of this biomarker in our sample is a little bit skewed. And we can easily test that. We can draw a histogram for the data. I'm here in Google Sheets, but it works exactly the same in Excel. So we highlight the cells and go to Insert. Here, go to Chart, and Google Sheet draws a nice histogram for us. And what we see is that indeed our suspicion was right. We have a skewness here. So the data have a sort of a long tail to the right. So they are positively or right skewed. And of course we know that when we want to do any tests or confidence intervals, our data need to come from a normal distributed population. And by the looks of it, this does not really look like a normal distributed population from which we have drawn the sample. Now, what we need to do really is to confirm this guess, and there is a nice test for that. It's called the Shapiro-Wilk test. And we can formulate, as always, we can formulate a null hypothesis and an alternative hypothesis. So in a Shapiro-Wilk test, let me make that so that we can see this properly. In a Shapiro-Wilk test, the null hypothesis says there is no difference between the population distribution from which the sample was drawn, so our sample here, and a normal distribution. So basically it says we took this sample here from a normal distributed sample, and any differences that we see from this normal distributed population, this skewness that we've observed, is just simply due to sampling error, which could happen. The alternative hypothesis, however, is that there is a difference between the population distribution from which we have taken this sample and a normal distribution. So in other words, the population from which we have taken this sample is not normal distributed, and therefore any observed differences are due to sampling error. So what we would do then is we would say we set an alpha value, and we would usually set this as 0.05 or 5%. And then we make a decision. We would calculate a test score, and depending on this test score, we would get a p-value. So, and if the p-value is smaller than the alpha value, so smaller than 0.05, we would say p is low, h naught must go. We reject the null hypothesis. And likewise, if the p-value for this test was larger than alpha, we would fail to reject the null hypothesis. Fail to reject null. Now, calculating a Shapiro-Wilk test is not for the faint-hearted, so it's not very easy to do that in Google Sheets or Excel. So luckily we can get an online calculator, and I will leave the link to this calculator in this description to this video. So all we need to do is we actually just copy the data. And so copy the data and go to this calculator. We clear any results here and clear the data. So here is this calculator, and we can just simply copy paste the data from our biomarker straight into this Shapiro-Wilk test calculator. And now we calculate the test statistic, and we see here we've got 13 observations. We get test statistics. We even get a sort of a histogram, and that basically shows more or less what we had, although this is not a true histogram, this is a bar chart. But what we get is also the p-value for this Shapiro-Wilk test. So I copy this p-value, and we can put that in here. So we get a value of 0.005. And this means this value, this p-value, is smaller than our alpha value of 0.05, considerably smaller. So we would reject the null hypothesis, and we would say there is a difference. So our guess was right, that this is a sample that comes from a skewed population, and therefore we would not be able really to do any tests or any confidence intervals that is based on normal distribution. So what can we do? Well, luckily we can do some transformations. So for example, we can take, instead of the raw values for the biomarker, we can calculate the log 10 value for these data. So that is fairly straightforward. So log 10 of these values, I just simply highlight the cells, close the bracket, and do the calculation, drag it down like that. So I've got now my log 10 value of the biomarker, and I can now try and perform the Shapiro-Wilk test. So I copy the data, I go back over to the statistics, I clear the results, and also clear this one here, and I just simply copy paste these log data now and calculate the Shapiro-Wilk statistics, and I get a p-value here. I will copy this p-value, and we can now put that p-value in here. So here we've got a p-value, and we see this p-value for the log data is 0.07. Now this p-value here is larger than our alpha, larger than 0.05. So this distribution of the log transformed data would actually meet the criteria for a normal distribution. So here, these data, we would say yes, they are okay, whereas these data here, we said they indicated that they are not from a normal distributed population. So this value is okay. Now there is another way we can do a transformation which is also valid, and that is the inverse of the biomarker. So equals 1 divided the biomarker here. And yes, we accept the autofill, so the program has already done that. So all we need to do is we take these data, the inverse data, and put them into our Shapiro-Wilk test calculator. Let's clear the results, clear this, and we add this one here as well. So here we've got our inverse data. Now let's calculate the Shapiro-Wilk test statistics, and we get the p-value, and what we see is yes. Let's copy that and put that into our p-values here. Yes. We get a p-value of 0.27, and again this p-value is larger than 0.05. So again we would say that this distribution here of the inverse values forms actually a normal distributed population. There is one more that we can do. So that would be the square root of our biomarker concentration. So that's the square root here. Let's calculate the square root of the data of our biomarker. Okay. And the program does the calculation. So here we've got the square roots. We just copy the data and go over to our Shapiro-Wilk. We clear the results. We clear the input and copy paste again. Here, so we've got our square root data, and let's see what the corresponding p-value is. So here we've got a p-value for our test statistics. Let's copy that and go over here. So here, let's put that in. And we get a p-value of 0.02. And of course, we notice that this p-value is smaller than 0.05, our alpha value. And therefore, we would say that this transformation actually leads to a distribution that is not normal distributed. However, we have two distributions, the log distribution, a transformation, the log transformation, and the inverse transformation that would give us the value, the p-value that indicates that these distributions are actually from a normal distributed population. And we then can use, instead of the raw data for the biomarker, we can use either log 10 or the inverse transformed data in order to calculate a mean, a confidence interval, or we can even compare the data in a t-test. So this is how we can do transformations of skewed data that are very clearly do not come from a normal distributed population. And with this log transformation or inverse transformation, sometimes also with a square root transformation, we can convert them into distributions that we can actually work with. So it would be absolutely safe to work with these two transformations and do some parametric tests. So I hope this makes sense, and thank you very much for watching.